Okay. So let's start then with the vectors. Imagine, for example, that I have a vector here. Can you see? Yeah. So this vector here, I'm going to say this is vector A. Okay? And what distinguishes this from a scalar, for example, I can write here something like this. Scalar vector. Okay? So, scalar, we only have the intensity or the value, right? Value, intensity is a bit... Okay, let me see if I can write better, sorry. For example, if you have a velocity vector, or the scalar of the velocity is going to be its value or the speed, right? Vector, you have more, so you have also intensity, but you also have one very important thing, which is direction. So with vectors, you also have information regarding direction, right? So for example, if you have here point A and point B, this vector A will tell you how to go from point A to point B in a straight line, right? So that information is included in a vector, but is not included in a scalar. The scalar will only tell you the norm or the intensity of this vector, right? It doesn't include any information regarding the direction. So this is basically the most important thing that distinguishes a vector from a scalar. And this introduces an additional problem, which is, okay, the vector gives us the direction, so we need to understand or describe that direction in a coordinate system. Okay? Right? So that's another thing we have to do with vectors. We have basically to for example, if I have here vector A again, I will have to say this vector A will have to have a coordinate system that I will say X, Y, right? I'm doing in 2 dimensions. I'm doing a 2-dimensional analysis. So this coordinate system here is going to be my referential, if you want, that will allow me to obtain the direction of vector A. And how do I do that? Well, I have to decompose the vector A in X and Y directions. So the way you do that is you draw parallel lines to the axis, okay? And then you say, this is my component in the X direction. I will call it AX is still a vector, right? And this is going to be the component of my vector in the vertical direction. I will call it AY. All right? So it's quite easy to understand this. You have a vector A in red. You need to have a coordinate system to describe this vector. And then what you just do is you just draw parallel lines to this coordinate axis. And the intersection of these lines with the coordinate axis will give you the location of the components of this vector, AX and AY. Right? Okay, so one more thing we need to understand is that this coordinate axes, x and y, in order to define, they are also vectors, right? This x and y, they are also vectors. So in order to define the direction of these vectors, we usually use a unit vector. We call sometimes versors. Okay? So if I do that, so I'm going to do that in black now. So I'm going to say that this unit vector I'm drawing here, I'm going to zoom in a little bit. I'm going to call this my I unit vector. So unit vector means the norm, the norm of this I vector is equal to 1. The norm or the intensity or the value of this vector is equal to 1. So it's a unit vector. So what is the information that we get from this unit vector? The information we get is the direction only, because its norm is equal to 1. And that direction is the direction of my x-axis, right? Same thing for my y-axis. I can also have here a unit vector in the y direction that I will call it j. Again, the norm of j is equal to 1. Is a unit vector as well. The only objective of this vector is to give me the direction of my y-axis. And then I can say something like this. I can now say that my vector A will have a component in the x direction, which is going to be ax. So this ax I wrote here in blue is basically what? Is the norm, or the, if you want, is the length of this ax vector here, is the length or the intensity of this ax vector. So this gives me only the intensity, but I need to have also the direction of this ax. How do I get the direction? Well, the direction is given by this unit vector I. So I need to multiply now this by my I unit vector. So if you look carefully, this product here will have information. So this is going to be my ax vector. A vector now, right? This ax vector is the same as this here. I will have information about the intensity of the vector, is this ax scalar, and I have information about the direction of the vector, which is this I unit vector, right? But this is not completed yet, because I need now to add, in order to obtain my vector A, in red, in the figure, I need to add now the y component of the vector. So I'm going to do in a similar way. So this y component is going to be ay, and I need now to multiply this by the unit vector along the y direction, which is my unit vector j. Right? So this product here, this is going to give me my ay vector. All right? Any questions? Yes.
So we can understand the difference between x and y.
Between this and this?
Yeah.
Yeah, this.
Why do you need both?
Sorry?
Why do you need both?
Why do you need both? Because we are working with vectors, right? Like I said here in the top, the vector here, you need to have these two, intensity and direction. You need to have these two informations, right? That's exactly what you have here. If you look carefully, here, this term here will give you what? Intensity. This term here will give you direction. All right? That's why you have two. When you multiply both, you have these two information. You have the intensity and the direction. Always like that, okay? So that's why you need here a unit. That's why you need I to be a unit vector. Because if it is not a unit vector, when you multiply I by AX, you will get a wrong intensity for AX, right? Right? If you multiply AX by 1, you will get AX, intensity AX, right? So, yeah. Okay. Now, what you can see here, you can see that we have AX plus AY. So if I add these two, I will have at the end my vector A. Correct? That is exactly, so I'm going to delete this. Let me just do this. So this is exactly what we are doing here. So I'm trying to reproduce here. So we have AX vector. So is this horizontal component here? This horizontal component. Can you see? And what I'm going to do is I'm going to include this vertical component AY. Right? I'm going to include it here, AY. Right? And what I'm saying here is that I'm adding AX plus AY, correct? That's what I'm doing here, right? So I'm going to do it here graphically. So in order to do it graphically, so I'm going to do the opposite, like I did in the opposite way, right? So I'm going to draw parallel lines here to this and to this, right? And then I just connect this point to this point, and this gives me my A vector. We call this the parallelogram rule, to add vectors graphically, right? Okay, so we saw here how to decompose a vector into its components along the coordinate axis, AX and AY. We saw then how can we obtain the vector by adding these two components, AX and AY. So this is a very common way of representing vectors. It includes all the information regarding intensity and direction of the vector. There is also an alternative way of representing this, which I tend to use more than this, which is I can say that my vector A is going to be represented by my X component, AX, and by my Y component AY. Okay? We call this the matricial notation. All right? This is the... Oops. Yeah, we call this the matricial notation. All right? So this is very easy to understand. So the first component here is the component of the vector in the x direction, is this one. Okay? Sorry, I'm just trying to compose this. While this component here, the second one, this one, is the component in the y direction, this one here. All right? Of course, if you have a vector in 3 dimensions, you will say, for example, if I have my vector A described in a 3-dimensional coordinate system, I will have a component in the x direction, AX, a component in the y direction, and a component in the z direction, right? Or if you want to represent it this way, I will have something like this. A equal to ax times I plus ay times j plus az times k, where k is also a unit vector along the z direction, okay? All right? So let's do one example. Imagine, for example, I give you this vector. This vector A. Let's do a two-dimensional analysis, two-dimensional example. So this is my x-axis. This is my y-axis. All right? You can sit here. There's available seats here. You don't need to be standing there. Okay, so, and I'm going to say that this vector A makes a 30 degrees. So this angle here, from here to here, is 30 degrees. All right? I want to get the components of A all right? So what I will say is that we have to decompose this vector along the coordinate axis. So I'm going to decompose A in the horizontal x direction. So this vector here, I will call it AX. And then I can say that AX you tell me, how much is the norm or the intensity, or if you want, how much is this length of this vector? Yes?
AX cosine 30.
A norm of A cosine of 30 degrees. So I will say, you know, norm of A gives me what? Norm of A gives me the length of my vector A, right? Gives me that length, or the intensity of vector A, right? So if I multiply this length, basically we have here a rectangular triangle, right? If I multiply that length, which is the hypotenuse, by cosine of 30, I will get, so what I'm saying is that if I do norm of A cosine of 30 degrees, like you said, this will give me what? This will give me is the norm of AX. The norm is always the intensity or the value or the length of the vector, right? So it gives me this length, right? Gives me this length here. Right? This length here is the norm of this vector AX in blue, which is basically the projection. So the norm of A cosine of 30 degrees is the projection of vector A in the horizontal axis, right? That's how you project a vector along a specific direction. So this is the norm, the scalar. I need now to multiply this by the unit vector, which is my unit vector I. So then I know that this norm of AX, or that length, is applied over my x-axis. So I get the direction, right? And I need to do the same thing now for the y direction. I need now to project my vector A along the vertical direction. So what I'm going to do is I'm going to try to obtain this vector here, which I will say this vector is AY, right? I will try to obtain this vector. And then I can say that, and then I'm going to add, sorry, this is AX, you're correct. Then I'm going to say AY is going to be what? Is going to be again the norm of A times what? Now, sine, very good, sine of 30 degrees. And then this is going now to be along my y direction, which is defined by this unit vector j, right? And then now I can say that my vector A is going to be what? Is going to be the norm of A cosine of 30 degrees along the I direction plus the norm of A sine of 30 degrees along my J direction, right? Or if you want, I can use this space here. I can say that my vector A is going to be equal to the norm of A cosine of 30. Sorry. I think I don't have too much space here. Let me try to get some more. So what I was saying is that I can now say that my vector A in matricial notation is going to be equal to norm of A cosine of 30 degrees, norm of A sine of 30 degrees. Right? Okay? So it's very easy. For example, if I tell you that, imagine in this example, I tell you something like this. Norm of A is equal to, let's say, 10 kilonewtons. 10 kilonewtons. Imagine this vector A is a force. And then I tell you, okay, the intensity of this force, or the bar of this force, is 10 kilonewtons. Then you can define the force vector A by just replacing here the norm of A by 10 kilonewtons, right? The x component is going to be 10 cosine 30, the y component 10 sine 30, right? So, and if you look carefully, we are completely representing a vector by including its intensity and its direction and adding the components to get the final vector, right? So far, any questions? Can we continue? All right, so what am I going to do now is I'm going to continue with the same vector A. So I'm going to write it here. This is now a very important thing, what I'm going to do now. So we have this vector A, and what we have been doing so far is we have been describing this vector A in this XY coordinate system. Right? And then what I did was, I'm just going to do it again here. We obtain this AX component, and we obtain this AY component, right? That's what we did so far. Now, what I'm going to do is, or you might be asking, why did I choose this coordinate system, XY? Can I choose a different one to describe this vector? I can choose any coordinate system, right? For example, I can now say that, okay, I don't want to use this coordinate system, but I want to use, for example, this one. Oops. Let me move this. Okay. All right, so I want to use maybe this one. So let's say this is x prime. This is y prime. It doesn't look like in the figure here, but x prime, of course, x prime is perpendicular to y prime, okay? They are orthogonal, they are perpendicular, of course, otherwise they will not be a coordinate system. They will not form a coordinate system, right? So, imagine, for example, I want now to describe my vector A in this new coordinate system, x prime, y prime. My question is, do you think the vector A that you have here in red, it will be different just because I'm describing it in a different coordinate system? Or it is going to be the same vector? Does it change? For example, if I'm saying this vector A, for example, is the velocity of a particle, okay? And this particle goes from, for example, this position A to this position B. Do you think that by changing the coordinate system that I'm using to represent the vector, do you think I am changing this velocity vector? Do you think I'm going from particle A to particle B, or I'm going to particle A to particle C, for example? Does it change?
No.
No, right? It's exactly the same vector, right? But something is changing here. What is going to change? What? Yeah, the components. Very good. What is going to change is the components of this vector, because if I want now to describe this vector A in this new coordinate system, x prime, y prime, what I have to do is I have to draw parallel lines to this coordinate axis, right? And then this is going to be my component. I will call it x prime. And this one is going to be my component a y prime. Right? You see what happens? And then I can now describe this vector A in red in these two different coordinate systems. I can do something like this. Look at this. I can say my vector A will be, I'm going to use matricial notation. If I describe this vector A in the original x, y coordinate system, I will get what? I will get ax, ay. Right? And if I describe this vector A in this x prime, y prime coordinate system, what I will get is, I will get the components ax prime and ay prime. Right? So, basically this tells us everything. The vector A in red here is the same. What is different is the components. Here in green color, you have the components in the x, y coordinate system. In blue color, you have the components of the vector in the x prime, y prime coordinate system. Basically, the vector is the same, but by using different coordinate systems, basically what we are seeing the vectors from a different referential, right? I can give you an example. For example, imagine something like this. Imagine this colleague here and this colleague there, okay? They are both looking at me. I am the same person, right? I'm not a different person because he's looking at me and because he's looking at me, right? But he's seeing my right face and he's seeing my left face. But I'm the same person, right? I'm not changing. But they are seeing me from different angles. That's exactly what is happening here. By using different coordinate systems, we are seeing vector A from different referentials, different angles if you want. Only the components change, but vector A is exactly the same. Okay? So this is an important thing. So, you will start now to understand that we are going to work with vectors always, and we need always to have a coordinate system to describe that vector. You are free to choose the coordinate system that you want. It's up to you. Many times we choose that for convenience because sometimes it's easier to represent a vector by choosing this coordinate system and not the other one, right? Okay? So, any questions? Everybody understood this? So this is the situation with vectors. We always have coordinate system that is very different from scalars, right? So if you are happy with this, I will then move to the next thing, which is dot product and cross product between vectors, okay? So let's start with the dot product. So imagine, for example, if I have vector A, if I have vector B, all right? If I have these two vectors, if I want to do the dot product between these two vectors, we represent like this: A dot B. Okay? That's why we call this dot product. And the result of this dot product is going to be a scalar, not a vector. Okay? This is very, very, very important. And that scalar is given by the norm or the intensity of vector A times the norm of vector B times cosine of the angle between these two vectors, this angle alpha. Okay? So as you can see, the result of this is a scalar, not a vector. Norm of A is a scalar, norm of B is a scalar, cosine of alpha is a scalar, so the result is a scalar. If, for example, there are other ways of doing this dot product. For example, if I say that my vector A is given by these components AX, AY, AZ. So I'm doing in 3D now. AX, AY, AZ. And for example, if I tell you that my vector B will have these components BX, BY, BZ. If I do the dot product A with B, I can do it in something like this. I can write this vector A. I can write the transpose of vector A, AX, AY, AZ. And then I do the dot product with vector B, BX, BY, BZ. All right? And basically, the result of this is going to be something like this. So I multiply, so I'm going to use colors now. I need to multiply the first component of my vector A with the first component of my vector B. And the result is going to be AX times BX plus, then I go to the second component of A, I multiply with the second component of B. Oops. Then you get plus AY, BY, plus, and at last you do for the Z component. You multiply AZ with BZ, and then you just add it here, AZ, BZ, right? So two different ways of calculating the dot product. They are summarized here. The first one is if you know the norm of these two vectors, A and B, And if you know the angle between the two vectors, you just multiply the norms with the cosine of the angle, right? And then you get the internal product, or the dot product. If you know the components of the vector in a coordinate system, ax, ay, az, bx, by, bz, you can do the dot product by multiplying the first component of each vector plus the second component of each vector plus the third component of each vector. This should be exactly the same at the end, right? So let's do an example of this. Let's do a very easy one. Let's say this angle alpha is 90 degrees. So I'm going to use here. So let's say I give you vector A. So vector A is this one, and vector B is this one. This is 90 degrees, they are perpendicular. I'm going to give some values here. So let's say norm of A, or the intensity of A is 10. I'm not going to put any units. Norm of B, 100. Okay? So basically we know we can define, now I'm going to define a coordinate system. For convenience, I'm going to say my x-axis is this one. My y-axis is this one. I can do that. I show you that I can use any coordinate system I want. And then if I do this way, it's very easy to represent or to obtain the components of these two vectors in this coordinate system. You might say vector A, the components are, so this is a 2D analysis. Vector A, the components are, so we have vector A is only has a component in the y direction, right? The component in the x direction is 0. And the component in the y direction is the norm of A, which is 10. This is my vector A. You all agree? My vector B, it only has a component in the x direction. And that component is, the norm of B is 100. So this will be 100, 0. Okay? Everybody's following? So if I do now the internal product using the first method, right, which is this one, norm of A is 10, norm of B is 100, cosine of 90 degrees is 0, the result is 0. Right? If I do the internal product A with B by using the components of the vectors, I will have what? I will have vector A transpose 0, 10. I will have vector B 100, 0. The result is going to be what? This times this, which is 0, plus 10 times 0, which is 0 as well. The result is also 0. Correct, right? And from this example, you can also see what is the meaning of the dot product. Dot product basically is the projection of one vector in the other's vector's direction. As you can see in this example, I'm projecting vector A. When I do the dot product A with B, what I'm doing is I'm projecting vector A in B direction. And as you can see, they are perpendicular, right? So that projection should be 0. Right? So that is the meaning of internal product. What I suggest we do now is we do the cross product now, and then we do a break. What do you think? Okay. It's good. I always have a okay in this question. All right, so let's do cross product now. So cross product So imagine I want to do the cross product of vector A with vector B. All right? The first important thing is the result of this cross product. So basically I'm going to say that the result is going to be a vector, not a scalar now. All right? So the cross product, the result is a vector. I call this vector vector C. And it's going to be obtained by doing a cross product of vector A. Cross product, we represent the product with this cross here, A with B. And the most important thing now is this property of the cross product, which is the resulting vector C is perpendicular. So I'm going to put it in red, sorry. So this vector C is the result of this cross product. And the result is going to be a vector. It's going to be a vector which is perpendicular to vector A and perpendicular to vector B. So I can say something like this. Vector C is perpendicular to vector A, and vector C is perpendicular to vector B. Right? You don't need to copy this because I'm going to make this available in Panopto, right? I think it's Panopto. I will upload this. So you will have Panopto or Blackboard, okay? Don't worry. I prefer you to pay attention, make questions if you are not understanding, all right? All right, so this is an extremely important property of the cross product. The result is a vector that is perpendicular to A and B. It's perpendicular to the two vectors that we are using for the cross product, right? And I'm going to show you that is the case. We are going to use the cross product, for example, to calculate the moment produced by a force, right? This is very convenient to be done in 3D analysis. For example, to calculate the moment produced by a force in 3D analysis, it can be very hard if you don't use the cross product. Because in order to obtain this cross product, so in order to obtain my vector C, what I'm going to do is, imagine I have vector A with these components, AX, AY, AZ. So this is my vector A, right? I can put it like this. This is my vector A. And I'm going to do the cross product of my vector A with my vector B, with components BX, BY, BZ. I'm going to do this cross product, okay? So this is going to be my vector B. And the way you do this is by doing a cross product of each component. So I'm going to explain it how we do that. So let's start with the X component of the vector, okay? So what we are going to obtain is, so this is going to be the result, my vector C. So let's work this first component here in the X direction. How do I obtain this component? I obtain this component by doing this cross product. AY times BZ minus AZ times BY. So I'm going to put some signals here. Oh, we can. So this component here is going to be, look at this, AY times BZ minus AZ times BY. That's why they call this the cross product. We are doing a cross product. Right? This is for the x component. For the y component, this one here now, the second component of this vector c. So I will try to erase this now. Let's see if it works. Okay, good. Now, for this second component, I need to do this cross product now. AZ times BX minus AX times BZ. There is a change in the signal here. But anyway, you will have here the final. So we are doing again the cross product. And AZ, let's do it blue. AZ times BX minus AX times BZ. This gives us the y component of this vector C. Now the z component, for the z component, for this component here, all right, I'm going to do this cross product now, AX times BY minus AY times BX. So basically, if I want z component, what I do is I ignore these z lines and I do the cross product with the other two components of the vectors. If I want the x component, I ignore this and I do this cross product. Right? You see how it works? If I want the y component, I ignore this and I do this cross product. It works like that. Right? So this component here, for the z component, what I'm going to do is I'm going to do this cross product here. And then that will be AX times BY minus AY times BX. This will give you the z component. Another good way to check is, if you look here carefully, we have AX, AZ, AY. So if you have here, for example, AX, AY, something is wrong in your cross product, okay? Same thing for the B here. We have BY, BX, BZ. They need to be all three different, right? All three different here, you see? So this gives you the cross product. I'm going to show you, just before the break, a quick example. Again, now we have to do in 3D. So let's say I'm going to write here so let's see, X, Y, Z. So X, Y, Z, 3D coordinate system. I'm going to define here two vectors, A and B, in blue. For convenience, I'm going to say my vector A is aligned with X. So this is my vector A. My vector B is aligned with Y direction. Okay? And I'm going to do the cross product of A cross product with B. The result, you know, the result needs to be a vector which is perpendicular to A and B. In this case, needs to be a vector that is coincident with Z direction, right? Look, A is X direction, B is Y direction. So a vector that is perpendicular to X and Y direction needs to be a vector in Z direction. Agree with me? So let's see if that is the case. How can I write vector A? So let's say vector A, for example, it only has component in the X direction. Let's say 10, 0, 0. Agree with me? This is a vector with only component in the X direction. Vector B only has component in the y direction. Let's say 10 as well in the y direction. So this is my vector B. So let's do the external product of A, 10, 0, 0. External product with B, 0, 10, 0. So let's do the cross products now. Let's start with my the x first. So I need to do this cross product now. This times this, which is 0, minus this times this, which is also 0. Agree with me? So the first term in the cross product is 0. Let's go to the y component now. For the y component, what I do is I ignore the y, and then I do this cross product here. This times this, which is 0, minus this times this, which is also 0. Agree with me? So the y component also 0. Now, z component, sorry. I ignore the z line here, and I do this cross product. This times this, which is 100, minus this times this, 0. So the result is going to be 100. And this, in fact, is a vector along this z direction, and vector C, for example, and the norm of C is 100. The norm or intensity of this vector is 100 and is aligned with z direction, right? Okay? So as you can see, the result of a cross product is a vector perpendicular to the two vectors used for the cross product. The result of a dot or internal product is a scalar. Very important. All right? No questions? So let's do a 5 minutes break. 7 maximum, sorry. Maximum 7. There was a very interesting question during the break regarding the cross product that I would like to address to all of you, which is, the question was, during the break, the norm, so basically the norm of the result of the cross product, the norm of this vector C, what does it represent? And what it represents basically is this. It represents the area. So we had vector A and vector B. This area here is basically the norm, or the norm of the result of the cross product. Right? And we can easily check in this example. Look at this. How much was this length here? This length is what? Is the norm of vector A, which is 10. By the way, how do you calculate the norm? The norm of a vector, vector A, for example, is the square root of x component square plus y component square plus z component square. In our case of our vector A, we have vector A, Ax is 10, then everything else is 0. So we have square root of 10 square, which is equal to 10. This is the norm of our vector A, which is exactly the same as our vector B. The norm of B is also 10. So if this is 10, the length of my vector B, or the norm of vector B, is also 10. So this area is going to be 100. 10 times 10. Which is the norm of vector C, the result of the cross product. Okay? So cross product has a lot of information. First, give us a vector that is perpendicular to A and B, and the norm of that vector is the area formed by the parallelogram between A and B. Right? Okay? I hope it answered the question. I don't know who it was, but... Okay, so let's move now. And let's start now to discuss the equilibrium of a particle. Right? So my plan now so we have more or less 30 minutes until the end of the lecture today. So I will introduce you the equilibrium of a particle, how to study that, what that means. If we have time to do one example, we will do it. If not, next Friday, we have 1 hour more. I will do that hour only solving examples with you about equilibrium of a particle, okay? So, in order to start the equilibrium of a particle, so far we have been talking about vectors in a very generic way. Now we need to talk vectors as being a force. Now, our vectors now are going to be forces, all right? So let's say, for example, I have here force 1. And I have here force 2. And I have here a particle. Let's say particle A. So these two forces, they are two vectors, F1, F2. They are applied in this particle A. And what I want to do now is I want to obtain the resultant we call R. I want to obtain the resultant of these two forces in particle A. Basically, this resultant is what? This resultant is I need to add F1 with F2, and the summation of these two forces will give me the total force in particle A, which we call the resultant. Okay? So basically, if I add these two forces, what I'm doing is I am adding these two vectors. So I need to draw a parallel line to F2, a parallel line with F1, right? So in this intersection, I will have this vector, which I call vector R, which is the resultant, which basically is what? Is the summation of F1 with F2. Right? So, here, below, I am adding these two vectors. In the figure, I am adding these two vectors, F1 and F2, graphically by using the parallelogram rule. So, this is equivalent. So, if I will say that this system is equivalent to having a particle A here and having only the resultant. Okay? So basically what I'm saying is original system with two forces F1 and F2 is equivalent to this second system here below, where we have the same particle A, and only one force applied to the particle, and that force, in order for these two systems to be equivalent, that force needs to be the resultant, or basically the summation of all the forces acting on the particle. All right? So we will have to do addition of vectors to get the result. Something we did today. Okay, so we have now a particle under the action of one single force, which is the resultant. How do I say that this particle is in equilibrium? So what I have to do is, I'm just going to write it here again. So for the equilibrium, of this particle, what I'm going to say is that this resultant needs to be equal to 0. All right? So, this is quite trivial. If we have a particle, if we have the resultant of the forces in that particle, if we say that resultant is equal to 0, then that particle will be in equilibrium. Right? Equilibrium means the balance of all the forces acting at that particle, that balance is 0 at the end. The particle stays there at equilibrium, does not move. Right? For example, imagine the particle is this pen I have here. I put the pen here on the table. It's not moving now. It's in equilibrium, right? Why? Because you have, what are the forces acting on this pen? You have the force of gravity, right? And then you have the reaction of the table on the pen. So the gravity will balance with the reaction of the table. So at the end, the summation of these two forces is equal to 0. And the pen is in equilibrium, does not move. Imagine now, I have the pen here. I still have the gravity force, right, applying on the pen. I'm going to release the pen. Not in equilibrium, right? Summation or the resultant of force is not equal to 0. We have only the gravity acting on the particle, on the pen, and then it falls down. It's not in equilibrium, right? So in order for a particle to be in equilibrium, the resultant or the summation of all forces acting on the particle needs to be equal to 0. Okay? Now, imagine, for example, that I give you this R, a vector like this. 10, 0, 20. These are the components of this vector. So what happened in the past, many of your colleagues tend to say, because they see a 0 in a component, they tend to say the resultant is equal to 0, which is wrong. In order for the resultant to be equal to 0, we need to say this component needs to be equal to 0, this component needs to be equal to 0, and this component also needs to be equal to 0. All of the components of the vector need to be 0, not only 1. Right? And why am I saying this? Because now you can see from our previous slide, for example, imagine I'm doing this example in 2 dimensions, right? So I will have a coordinate system, x, y. This y is not very good. Let's do it again. We have a coordinate system. I'm going to say there's a resultant, so maybe I can delete this to get some space. I can say that this resultant is going to be the addition of vector f1, which will be f1x, component in the x direction, plus f1y, plus vector f2, which will have a component in the x direction and a component in the y direction. So the result is going to be f1x plus f2x. And here we'll have f1y plus f1y. Sorry, f2y. So basically what I'm doing is I am adding 2 vectors. The way we do that, add 2 vectors, is by adding component by component of the vector. So adding component f1x with f2x, then I get the x component of my resultant. Then I add f1y with f2y, and then I get the y component of my resultant, right? And then what I have to say is I'm struggling a bit with space here. So let me do this way. So maybe I can delete this. Let me see. If I delete, I'm going to delete this figure and work only with the vectors. Maybe I can move this guy. Let me see if I can do it. Oh, I can. Very good. All right. So now what I'm going to say for the equilibrium, what I'm going to say is the resultant needs to be equal to 0, or, taking our example, what I'm going to say is this vector here, which is the resultant, I'm just going to put it there. I'm going to say f1x plus f2x, f1y plus f2y. This is my resultant vector. Needs to be equal to 0 so that my particle is in equilibrium. Right? That's what's going to happen. So what I'm saying here is that x component needs to be equal to 0 and y component needs to be equal to 0. We are doing in 2 dimensions. If I'm working in 3 dimensions, I will have here a third row. Components in z direction, they also will have to be equal to 0. And why am I doing this? Because in this case of 2 dimensions, you can see that basically we will obtain 2 equilibrium equations, not only 1. What are these equilibrium equations? The first one is the components in the x direction of the resultant needs to be equal to 0. That gives me 1 equation. Second equation is the components in the y direction of my resultant vector equal to 0. 2 equations in 2 dimensions. If I am working in 3 dimensions, I will have 3 equations. And why is this important? This is important because this is important, and I'm going to show you why this is important in one example, okay? Right? So let's do one example now. I'm going to pause to stop this video here, and we are going to do one example now, right? Just apply this. Sorry, I forgot to put it right. Okay. So basically, like I was saying, these bars, they all have forces applied. And all these forces, these vectors, as you can see, they are converging to point O, right, in the figure. So basically, what I'm saying is that we can just take point O. I'm going to put it here. This is point O. And we can represent all the forces that we have applied on this point O. So we will start with this first one here. 8 kilonewtons, which is, so I'm going just to put this force over here. I'm going to say this is 8 kilonewtons. I'm not writing now a vector in top of this 8 because this 8 kilonewtons will give you the intensity or the value or the norm of this force, and the direction is given by this arrow, right? So it is applied in point O. What else do we have? We have this force now here. Can you see? Which is a force T. Is a tension T, which is unknown. I think is unknown. But anyway, is a force that is also applied at point O. I'm going to represent it here. T. Okay? And this angle is 30 degrees, right? This is not very good. Let me try to... I need to zoom in a little bit. 30 degrees. This is better, right? Okay, what else do we have? we have now this force F, this one, that I'm also going to include it here, F, which is also unknown. We don't know the value of this force. And we have the last one that we have is this force of 5 kilonewtons, which is a force applied here, right? Five kilonewtons, right? And that's all we have. So in this particle, we'd make it a little bit bigger. In this particle, we have all these forces acting on this particle. So what am I going to do now? Well, because I have vectors here, I need to have a coordinate system, first of all. So I'm going to say this is my x-axis, this is my y-axis, right? And what I'm going to do now is that I'm going to obtain the components of all these vectors in this coordinate system. I'm going to add these vectors component by component, and then at the end I'm going to say that resultant is going to be equal to 0 to be in equilibrium. But before we continue, I would like to take this example to introduce you a very, very important thing in statics and dynamics and everything you are going to do from now on in uni, which is the free body diagram. I'm going to write it here, free body diagram. Many times we represent this by FBD. For example, in dynamics in term 2, the lecture last year, they asked you explicitly to do the FBD. What is this free body diagram? Why is this so important? This is the secret to solve all these problems. If you understand this, that I did here in this example, you will have your life much easier. What I did was, I took point O from this example. This point O that you have here, I took this point and I isolated this point from the structure, right? And then I built this scheme that you have here, right? So basically I isolated this point O and I represented all the forces that we have acting on this point O. Right? That's why we call this free body, because I isolated this point from the structure. I release it from the structure. I isolated it. So that's why we call this free body diagram. And then we need, of course, to represent the forces and have the coordinate system to describe the forces, and then just add all these forces together and say that summation equal to 0 and problem is solved. This will be very important for the equilibrium of 3D rigid bodies, for trusses, method of joints, method of sections, beams, everything you're going to do in year 2. For dynamics, you will have to do this in dynamics, because in statics we say summation of forces equal to 0. In dynamics you say summation of forces equal to mass times acceleration. That's the difference, right? So you will have to do these free body diagrams. If you know how to construct these free body diagrams, you will be very good in this model, trust me. All right, so let's continue. So free body diagram, that's what we did. So what is the next step? What am I going to do now? I'm going to define all these vectors. So I'm going to start with this 8 kilonewton, okay? So this one here, I'm going to define this vector first, all right? This 8 kilonewton, so I'm going to use matricial notation. We have a component in the x direction only, which is equal to 8. Agree with me? This is a 2D problem, so we have, this is my 8 kilonewton vector. I'm going to define now this f vector. So this f vector, I'm going to include it here now, is the next step. So I'm going to add, because I need to add all the vectors to get the resultant. So how do I obtain this f vector? Well, this f vector, if you look carefully, is aligned with my y direction. So I have only component in the y direction. And I can say then the x is 0, y direction I get f, because it is an unknown. I don't know the value of this f. Next vector I'm going to consider in the analysis is this 5 kilonewton here. I'm going to work this 5 kilonewtons vector now. All right? So I'm going to decompose this 5 kilonewton vector in x and y direction. Let's start with the x direction. How do I decompose this? So I forgot to include here this angle is 45 degrees, right? This is 45 degrees. How do I obtain the x component of this vector? I'm going to use the red color here. So my x component is going to be this 1. Right? And I can say that this component here is, you tell me, what do you think?
5 cos 45.
5 cos 45. Very good. Right? What about the y component?
The same.
Yeah. So this y component is going to be also 5 cosine or sine 45. Is the same thing. So let's put here sine. Right? And now I just need to take these components in red color that I just draw there and include them here, right? So I'm going to say, starting with the component in the x direction, as you said, is 5 cosine 45. And the component in the y direction, now a very important thing, what do you think it needs to be? Plus 5 sine 45 or minus 5 sine 45? Minus, very good. Look, this vector, this component here in red, this component, the vertical component, it has the opposite direction with my y-axis. So for that reason, it needs to be minus. So I'm going to put here minus 5 sine 45 degrees. Okay? Everybody understand? Yes?
See, force A, put an 8 as well.
No, for the first one, the 8 kilonewtons.
Yeah.
Yeah, look, the 8 kilonewtons, this one, the force has the same direction as x. When it has the same direction as the coordinate axis, it needs to be a plus. When it has the opposite to the coordinate axis, is a minus, all right? Okay? All right, so we need now to do the last vector we have to decompose is vector t. So I will try to delete this bit here. Let's see if I can. Otherwise it becomes very confusing. Okay? So we need now to decompose this vector t. So I'm going to use now the black color. We do in a similar way. So we will have to draw these parallel lines to the axis. So this black one is going to be my x component, and this one is going to be my y component. Both of these two components are opposite with the coordinate axis, right? So they need to be both negative. Okay? You all agree with me? So this component here is going to be, you tell me, what is the norm of this horizontal component?
T cos 30.
T cos 30. Very good. So T cos 30 degrees is this component. Now this one here You tell me now. T sine 30. Very good. T sine 30. So don't forget this is the length or the intensity of these components or the norm of these components. Now we need to put this. We need to add this to our vector, right? So starting with the horizontal one, starting with this one, this component is opposite with x, so it needs to be a minus, right? So I will have minus t cos 30 degrees and then now this one, the vertical component, is also opposite with my y-axis, so it needs to be a minus as well. So it's going to be minus t sine 30 degrees, right? You all agree with me? And that's all we have, right? So if I add all these vectors together, I will have the resultant of the forces in this particle O, and then I will have to say this resultant needs to be equal to 0. So this needs to be equal to 0, 0. All right? Okay, so what I'm going to do now is I'm going to add all the components. No, sorry, I'm going to add, for example, for the x components, I'm going to add all of the x components of all vectors together. So I'm going to build my system of equations, right? So let's start with this x components. So I'm going to take these x components and say, so I will have what? I will have 8 plus 5 cosine of 45 degrees minus t cosine of 30 degrees needs to be equal to 0, right? One equation. One equilibrium equation. Second equilibrium equation is, if I now look at the y components, these ones here, and just write them down. So we get f minus 5 sine of 45 degrees minus t sine of 30 degrees equal to 0. All right? And look at this now. We have what? We have here a system of equations. Two equations for two unknowns, right? What are the unknowns? T and f. Two unknowns, two equations. We just solve this system of equations. We don't need to solve it here. It's quite basic. We solve this system of equations, and then we obtain the value of force T and the value of force F in this structure. That guarantees that my particle O is in equilibrium. All right? You see how it works? So, the idea, so we are basically finishing. The idea of this lecture today was to introduce you with vectors. I want you to be very careful with vectors. It's very important to understand very, very well vectors. How to decompose a vector, to get the components, do the internal products, external or cross products, add vectors together, get the resultant of the forces, and then the equilibrium equation for a particle is quite easy, right? Okay? So next Friday we are going to do only examples of equilibrium of particle, okay? So I hope you enjoyed. See you next Friday then.